2. And as Parvati ma'am said, asked about the power and delay, these are also available with some crack version, the latest one, the 20 version. And those are little bit complicated compared to this 16, but all the videos are available, right? And it is, it needs some kind of revision. Means revision should be there. If you will revise those things, you will sit continuously on this particular 10, you can explore so many things, right? It is not possible to have all the things in 1 hour, right? So those who are interested, they can start with the 16 version, and if they wanted to do in higher technology version, then they can either they can manage to have the crack file for the latest technology, or they can ask to any you can say any researchers in ResearchGate or through ResearchGate, because they are helping, they are giving this latest technology file. Okay, now we'll come to the presentation. Ma'am, can you
yes,
for the presentation, so that I can
Mr. Akash, yeah.
Yes.
Will you please answer? Sir, one question here. Yeah, from my side, sir, what are the libraries can be possible with this TENA tool, sir? Up to what technology?
Yes, because this one is whatever we are using, that technology, this technology is basically 250 nanometer technology. That is quite older, or you can say no one is, because if you are talking about above 100 nanometer, then it is no more nanometer, right? And this one is 250 nanometer. But for the you can say for the starting your research, starting your circuit simulation, you can use this one. But if you will publish with this 250 nanometer technology parameters, no one is going to entertain. So for that, what I'm saying, you just go for the latest paper in ResearchGate. Those who have published the latest paper, you just contact to their author and you just request them to provide the technology file, latest technology file, for example 32 nanometer technology, 22, 12, whatever. And sometimes they are giving. If you will include those files, then you can able to simulate those things, right?
Yes, sir. So I can back the presentation, sir.
Yes. So I will complete all those things quickly, so that it is having a exposure kind of thing. And although these slides are with you, ma'am, if somebody will ask me, just provide those slides to them.
Definitely, sir. Sure.
Yes. So I will go quickly and just go for next one, for buffer. Since we have already designed, as I told you, this is the simple basic steps, that how you simulate those things and how you will analyze those waveforms, right? So since we have already demonstrated this CMOS inverter, so when we'll go for this buffer, then what is buffer? Buffer is simply combination of two inverter. So when we'll have these two inverter in this fashion, whatever is showing here, then you will simply have a buffer circuit. So next. Go for next. This is also the basic things. Go for the next one. Yes, you can see here, since you have already designed the first part, the inverter, and when we'll have arrangement like this, and in the beginning I told you, when you will go for this particular EDA tool, then you must have the design tool. If you don't know how to connect, if you don't know where we have to connect those things, then you can't use this tool. So this is the typical design, and the same design, if you will design in the Tanner, then you are able to have this kind of waveform, input and output. So you can go for next. So here you can see this buffer circuit where I have used two inverters, right? And the, you can see the same steps we have followed, that we have applied what is happening in buffer. We are applying 0, we are getting 0. We are applying 1, we are getting 1. The same input, the same output. So what we are doing, you can see only one input pulse is there, which is applied at the first inverter, and we are observing the output from the second inverter. So we have used this two print voltage. So two print voltage means we will get two waveform, the input and output. And when you will simulate this circuit, you will have the waveform in this way. You can go for next one. Yes. So this is the actual waveform when we will simulate this buffer. Simply here you can see when we'll apply 1, we are having 1. When we'll have 0, we'll have output in terms of 0. So that becomes a simple buffer. Go for next. In same way, you just go for the NAND gate. As we have discussed in the beginning that this CMOS logic is complementary logic. So first we'll try to simulate the NAND gate, NOR gate, and since these two are universal gate, and once we have demonstrated this NAND NOR, then you can design any circuit. So this, but you must know how to design this NAND. So how will design this NAND? In pull-up network, this PMOS comes in parallel, and in pull-down network, this NMOS comes in series. So this is the actual implementation of NAND gate, and you must know this one. Then only you can able to design in Tanner, right? Since this is the NAND gate, so you can verify your truth table through the waveform, right? Next. In same way, we'll go for the NOR gate, but things will change in NOR gate, because in NOR gate we will have this PMOS in series and this NMOS are in parallel. And since this is NOR gate, so we required two inputs, so we are having two inputs, V1, V2, and we are getting the output. Next. So the circuit, then only you are able to design the circuits in the Tanner. Now this is the typical. Someone is saying something?
Nothing, sir. You can continue. Yeah.
Okay. So this is the typical NAND gate implementation in this Tanner, where you can see we have two MOSFET, two PMOS, and we are having two NMOS in series. These two PMOS are in parallel. So according to that design, as I told you, you must know the design. Then only you are able to draw those circuits. So here, what will happen? We are having two inputs and we are having one input. We just recall that table of two input NAND gate. So we have applied two pulses here, two inputs, input 1, input 2. And according to that design, that A, for example, if we are using A, B, then simply this is A, this is B, this is A, and this is B. The first upper one, the PMOS is having AB. You can see this one is A, this 2 is B, this 1 is A, and this 2 is B at NMOS side. And this particular VDD is coming in the same way, whatever we have considered for the inverter. And once you will simulate this particular NAND gate, then we will have the actual output. Go for next. Okay, this one is typical NOR gate implementation, where this PMOS, two PMOS comes in series, and these two NMOS comes to the parallel. Since we are having two inputs, you can see. You can use, as we have discussed, when we are selecting that instance for those, you can say, voltage sources from elements, then you can select the different pulses here. So here it is, you can say fixed pulse. Yes, next. Now we'll see the waveform. Yes. So this is NAND gate output. You can see the first two is your input, the red one and the, you can say, the green one. Third one is your output. So you can see, you just recall the NAND gate. What will happen in 0 0? We are getting 1. 0 1 1. When we'll have 1 1, it becomes 0. This third, you can say, sequence. Whenever we are having 0 1, we are getting 1. And once again, you can see whenever 1 1, it becomes 0. So this is the actual NAND gate output. In same way, we'll go for the NOR gate output. So go for next. So here you can see, you can recall the truth table of NOR gate. When we'll select 1 1, we are getting 0. When we'll select 0 0, we are getting 1. So whenever 0 0 is coming in these two inputs, we are getting 1. And whenever, and other than this, we are getting 0. 1 1 0 0 1 0. It's very simple. Yes, next. Go for next. Yes. So since we have already designed, yes, the first, before that one, previous slide.
Screenshots.
Yes. Now, if you are going to design a AND gate, then first you have to analyze how you are going to design AND. Since you have already designed this NAND and inverter, so NAND plus NOT, this is known as AND. So what we'll do, simply we'll design this NAND plus NOT. So next, in next slide, it is designed in that way. You can see. Here you can see, this is the typical NAND gate implementation, and this is a simple inverter. Since this is also 2 input AND gate, so we have selected 2 input pulse, 2 input pulse signal, and only one output that is coming from this particular point. So in this, we have selected this 4 print voltage. 2 is for input, 1 is for NAND, and 1 is for AND. And when you will go for this particular waveform, then you can easily identify the truth table of this AND gate. We will put AND gate. Go for next. So this is the typical CMOS AND gate. We have already seen this. These two are, first two are 2 inputs AB, third one is your NAND, and fourth one is AND. So whatever we are getting here, same thing we got it. So this is the typical waveform of AND gate. So for next, same way we'll go for OR gate. OR gate means NOR plus NOT. Go for the circuit. Here you can see this circuit is representing the first, you can say, left hand side is representing the NOR and right hand side is your simply inverter. So when we'll simulate this one, you will get the OR gate waveform, which is illustrated in next slide. Go for next. Now you can see. Now you can see the waveform of OR gate. So it is almost similar way to design AND gate, right? Now we'll go for quite a complex circuit, that is half adder. So can you go for next one? Yes, and as I told you that before implementing the circuits on this scanner, you must know the design. So this is the typical half adder. I'm not going to discuss the half adder in details, but yes, in half adder we are having sum in terms of A XOR B. So it is like this. So, but if you will arrange in this way, it is still A XOR B, right? And carry is simply AB. So for carry, we are having a particular this AND gate, NAND plus inverter. But here what we'll do, you can see here A XOR B. This is a typical implementation of A XOR B, where A bar B, A bar B. So these two are coming here, AB bar, and whatever is, as we have seen in AND and OR, whatever is series in pull up, those the same thing is parallel in pull down, and whatever is series in pull down, those becomes in parallel in your pull up network, right? So this is the typical implementation of half adder. Now if you will implement the same thing in tenor, you will get the half adder output. Go for next. Now you can see the typical implementation of half adder circuit. So what I did here, I have designed this one is A, so I have designed A to A bar, B to B bar, and according to A bar and B bar, you can see the circuit, somewhere A bar is required, somewhere B bar is required in this particular A XOR B, and this second one is typical AND gate implementation, right? So if you will implement your circuit in that way, which we have discussed in the last slide, then surely you will get the output of half adder. Half adder means you are having two inputs and you are having two outputs. Means you have used these four print voltage options. Two is for inputs, two inputs, and two print voltage is for sum and carry. Right? So next. Here you can see the first one is, first two are the inputs A, B, third one is your carry, fourth one is your sum. So what will happen in half adder? Half adder means when we'll have a different inputs, then we'll have the output. That is the concept of XOR gate. And when we'll have the same inputs, then we will have 0 output. Now you can see 0, 0. So at 0, 0 means we'll get the 0 output and there is no carry. 0, 1. Then we'll get the 1 output and there is no carry. When we'll have 1, 0, in this case also we are getting 1 as output and there is no carry. But you can see in this fourth one, fourth P, that 1, 1, if we are having this 1, 1, then we are getting 0 as a sum, and in that case we are having carry. So this is the simple, justification. Through that you can justify that your circuit is 100% right. Okay. If you will implement something different, or if you will miss some part, then you won't able to have the outputs. Now this one is quite complex. This is full adder using CMOS logic. So what is full adder? Full adder is having 3 inputs, and obviously since this is the adder, so it will have 2 outputs, sum and carry. Now you can see this is the typical design of full adder by using CMOS logic. So that's why I'm saying you must know the design part, then only you can design those things in tenor. Right. So from this part we are getting the carry, and from this part we are getting the sum. Now you can see we have started from the inverter. The simple 2 MOSFETs are there. Now you can calculate, you can count how many numbers of transistors are present in this full adder. right? So now you can think this is the simple full adder. If you will go for the 4-bit full adder, then what will happen? Number of transistors is going to be increased. So later on, I have not discussed those things. You can use those things as a block, and you can call those blocks. You can use header, call and save those as a block. You can call those blocks 2 times in a full adder. And if you are going for 4-bit full adder implementation, then you can design this full adder by using 2 half adders, and you can design 4-bit full adders by using 4 full adder modules. And this is the way, hierarchy wise. Otherwise, it is not possible to accommodate all the transistors in a small window, right? But this full adder is possible to design in the same window. So we have designed those things. The next one, go for next. So this is the typical design of this full adder circuit. In same way, we have designed, which we have started in the inverter. If you are having that design with you, then you can implement as it is in this channel without any fault. And if you will implement, then you will have the actual results in terms of waveform. Right? So how many inputs are there in this? We are having simply 3 inputs, A, B, C, having 2 outputs, sum and carry. So you can see we have considered this 3 as this 3 print voltage. It is smaller one, but it is visible. And this 2, the right hand side, is considered for the 2 output sum and carry.
Sir, a small question from
Yes.
from
Yes,
a small question. As the number of transistors are increasing, the design also clumsy. Do we have an option of creating a symbol? Symbol in the sense,
Yes.
like once we create half adder, we can make it as a symbol. And
yes,
yeah.
I discussed those things, ma'am. It is there in that Tanner tool. Actually, what you will do, for example, if you are going to design a 4-bit adder, right? Then what will happen? We can design a simple half adder. We can make as a model. You can see in the library. You just call that model 2 times. That 4-bit full adder. Then you just call that model 4 times. Yeah.
Yes, sir. Got it, sir.
To have this output.
Sir, your voice is breaking.
Voice is breaking.
Hello.
It's fine. Is it fine?
Yes.
Is it fine, ma'am?
Yes, sir. Yes, sir.
Is it okay? Okay, fine. So this is the typical, you can say, whatever we have discussed, full adder, A, B, C, and this is the sum and this is the carry. You can analyze those things whenever 1, 0, 1. In that case, we are having 1, 0, 1. In this case, we are having carry as 1 and sum as 0. In same way, if you will go for the truth table, then this you can say waveform is justifying all the truth table entry, starting from 0, 0, 0 to 1, 1, 1. Yes. So after that, we have seen all those things. But since yes, this is quite interesting. 4:1 multiplexer. This is the typical 4:1 multiplexer. And if you are going to design, then it will take so many AND gates. You can see 4 3-input AND gates, 2 NOT gate, and 1 4-input OR gate. But if you will design these things by using transmission gate, and generally people are preferring multiplexer by using transmission gate. Transmission gate is simply combination of NMOS and PMOS, and it is easier to design. So if you will go for the transmission gate implementation of multiplexer, then it requires minimum number of transistors compared to implementing by using these basic gates. You can see we are having 4 3-input AND gates, 2 NOT gate, and 1 4-input OR gate. So it is quite complex. That's why we will use this 4:1 multiplexer. We will implement this multiplexer by using transmission gate. So we'll just go for next.
Yes, phone చేశాడు. Yes.
No, go for next one. This is the second slide. Scroll down. Yes, next one. So this is the typical 4:1 multiplexer circuit by using transmission gate. Here you can see only 6 transmission gates are required to implement this 4:1 multiplexer. Basically, in transmission gate, this one is the upper one is considered as the NMOS, lower one is PMOS, NMOS, PMOS, NMOS, PMOS. In same way, if you will implement this particular design, then you will have the actual 4:1 multiplexer output. Go for the circuit. Yes. So this is the typical implementation of this particular 4:1 multiplexer. So what will happen in 4:1 multiplexer? We are having 4 inputs, we are having 2 select lines, and these 2 select lines are, for example, there are 4 options in this select line: 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. So we need 2 inverter kind of operation with that select lines. That's why in that design 2 NOT gates are there. Right? So what we'll have? Simply, we are having 4 inputs, we are having 2 select lines, those are also considered as the input, and we are having 1 output. So how many waveforms we will have? 4 inputs, 2 select lines, and 1 output. So total 7 waveforms will be there in this 4:1 multiplexer output. Total 7 waveforms. So you will be able to see all those 7 waveforms in the next slide. Go for next. Now you can see here all these 7. So A, B, C, D is your 4 inputs. This S0, S1 is your select lines, and this one is your actual output. So you can see clearly, based upon this select line, we are having outputs whatever is available at the input. Now you can see when we select 0, 0, what will happen? 0, 0 means we are selecting the A input at the output. So A is 1 here, so it is reflecting at the output. So it is still 1. Now you can see in this case where we are getting 0 output. So in this case we have selected, you just see when we are getting this 0. In that case we can verify whether it is correct or not. In this case the select lines are 0 and 1. 0, 1 means we will go for the second input. What is second input here? Second input is B. So B is 0 here, the same input is reflected at the output. In that way you can verify and it is 100% right. Because it won't give the wrong waveform if everything is fine. Okay, next one. Now the D flip-flop. Actually, till now we have discussed about the combinational circuit. So when we'll talk about the sequential circuit, then we'll have the flip-flops you can say the flip-flops are considered as the basic building block of sequential circuit. And in general, we are using D and T frequently for the register and the counters. So that's why I have considered this D flip-flop. What is D flip-flop? If we are going to implement, since we have started through this CMOS logic, since we have started with this inverter, then first we know how to implement D flip-flop by using this NAND gate. So if you will, other than this NOT gate, if you will see, then simply this is JK flip-flop, where this J and K are sorted by this inverter. So inverter is between J and K. Now it becomes D. Why we have considered this one? Because it is widely used in the sequential circuit, D-type flip-flop. That's why I have considered this D. So this is the typical structure. Now you can see 1, 2, 3, 4. Out of these 4 NAND gates, 2 NAND gates are 3 input configuration, 2 NAND gates are 2 input configuration, and there is 1 inverter. So if you will implement all those things, you are able to have this D flip-flop output. So go for the next. Yes, so this is the typical implementation of that D flip-flop circuit. Right? So you can see this is the first 3 input NAND gate. 3 PMOS are in parallel, 3 NMOS are in series, and this is the another 3 input NAND gate, 3 PMOS, 3 NMOS. And this is typical 2 input NAND gate, this is 2 input NAND gate. And according to that connection, we just connect all the wires. And here, if you will connect all the things, then simply you will get the output. Right? So go for the output. These are quite complex, but if you will do sincerely, everything you will get. Yes, now you can see here. The upper one is clock. This is D. This is the Q. This is the QR. Third one is QR. This is Q. So basically our main output is this fourth one. Right? Q. Q bar is simply the inversion of Q bar. Q. So you can see, as we know that the output of flip-flop depends upon the clock signal. Whatever is clock signal, we will get the output accordingly. Now you can see in clock there are having positive edge clock and negative edge clock. So this one is positive edge clock. So what it means, whenever we are having a positive edge, the output becomes changed. Now you can see this is output. Sorry, the lower one is output. This D is your input. In this positive clock, input is 0. So what we are getting? We are getting 0. But in same positive clock, this input changes. You can see the second pulse of this input D. At the same positive clock, this input is changes to 1. At that time, this output becomes 1. Because this output is changing from 0 to 1. Now it becomes 1. But after that, since this clock is negative clock, it is no more at positive. So what will happen? This transition will not change. Whether irrespective of input. Input is 0, 1, but it is still maintain the last stage. Right? Whenever it will have, you can see the third pulse of this clock. Whenever it will have the positive clock, at that time, according to that input signal, the D signal, it will change. Now you can see at this clock pulse, this D, G, it becomes 0. At the same time, at this clock this becomes D becomes 1 and 1 the positive. Clear? The logic behind this one. So it is the this
Repair it to
Hello, sir.
Hello, sir.
counter.
Hello.
Yes, ma'am.
Hello.
Hello.
Counter and registers also.
I think the
Yes, ma'am. Tell me.
I think the presentation.
I think the presentation is done with this last slide, sir. Nothing.
Yes, ma'am. Yes, it is over. So go for the last slide. Last slide is simply.
Previous one.
Previous
Yes,
one.
ma'am. Yes.
Previous.
So now it is.
on the page.
Hello.
So any question related to this one? If you will try in that way, you won't able to find any kind of error or any kind of difficulty while simulating in Canner, right?
So, sir, if the presentation is over, so we can.
I think no more slides.
I think no more slides, sir.
This is the last.
This is the last
No
one, right?
slide.
Oh, okay.
Chat box question.
Okay then. Stop
Any
sharing.
questions?
Any questions?
Yes.
Participants.
Chat box.
There are questions in the
Please, and how to measure delay and power consumption?
chat. Please, how to measure delay power consumption 1%, and how can we calculate delay area power dissipation from other person? Tarsana is one, Nati Ravi is another person. Like there's some questions.
Yes, as I told you. Yes, I think you have asked the same question, Parvati ma'am, that how to calculate this power at area. As I told you, when you will go for the licensed one, then
Yes, sir.
you can able to calculate those. Yes, and all the videos are available. How to
I
go
think
for
we can go for
that?
some conclusions on this. So, with yeah.
With lot of patience,
With lot of patience, the participants have done this session.
Yes.
And
hands-on session really it was went on as a hands-on session only. Maybe at the beginning some glitches have come, but
like it's a hands-on session. Really, it is maybe at the beginning glitches have come, but you the glitches we have able to see the participants' involvement in the session. I hope completely
Yes.
from the participants only we have seen the what is the outputs and all. So I think
with the complete session
participants
inputs.
have gone.
So thank you so
With the
much,
complete,
sir,
session
for your kind
inputs.
cooperation and
Yes.
excellent
The
session.
kind cooperation and excellent session, hands-on session.
Though
Though the glitches are there, so we could able to complete this and finally we have able to make us participants to understand well about the
they have done some
tool and
experiments
they have done some experiments also
in this session itself.
in this session
Thank you
itself.
so much, sir.
Yes, ma'am.
So thank you so much, sir.
Okay, ma'am.
And the participants for tomorrow's session will start by 9:30 sharp. First session.
Okay, ma'am. So
So
can
30
I-
short
Yes, sir.
first session.
Participants, thank you for
Participants,
listening patiently.
thank you
about
for
the
listening
session
patiently.
and- Yes. Yes, sir. Yes, sir.
Ma'am, I
Thank
have
you.
a doubt.
Yes, you can ask.
Yes, sir. Yes, sir. Thank you.
Participants, tomorrow will.
Participants, tomorrow we will start.
Library.
Sir, one question.
If I have
Sir, one question.
For this, sir, I will let you.
Sanjit sir, yeah.
Yes, someone is asking.
Please
Yes,
carry
tell
on.
Please
me.
carry on.
if I have a 45 nanometer library,
Yes.
and can I use that library in 16?
No, sir.
Okay.
No, you cannot use 45 nanometer in this one because this particular 16 version is for 250 nanometer only. That's why I told you, you just go for the latest one, that is 20, 10 or 20 version. In that they have used the latest one.
Okay. And sir, how to change the frequency of that signals, right? We are selecting that A and B signal.
Yes.
How we are changing the frequency? Because
No,
if they have same, then we will not get that right 0001.
yes.
So how we are
Applying the clock.
Applying the clock
cycle will be different.
cycle will be different. I think
Yeah.
the clock cycle should be different.
Yes, cycle will, you can, for example, if you are having 3 inputs A, B, C, then you just change their cycles.
On cycle and off cycle time duration we need. Yes.
okay tool we have that.
Yes. The options are available.
Okay, thank you.
Yes.
Yes.
Excuse me, sir. Ma'am,
Yes.
one more question can
Yes.
I ask?
Yes, yes.
Yes, please. Yes, please.
Is it possible to design a FinFET circuits in Tanner, or only CMOS circuits we can able?
No, ma'am, you can use. That's why I told you, na. But it is a fusion of back end and front end. So what you will do, that you have to develop a GUI code for that FinFET in your
Okay.
TCAD or in your any visual TCAD or in your Syntorus TCAD, and you can you can import that file into this Tanner.
Okay, sir. Can I use Verilog for that, or specifically Centauros TCAD only I am supposed to use?
No. Here Verilog there is no use of Verilog. You can go for TCAD. TCAD, that is Synopsys TCAD or Visual TCAD. In that you have to design a MOSFET, a single MOSFET, P-type and N-type, by using FinFET technology.
Okay.
FinFET technology or CNT-FET technology or TFET technology, right?
Okay, sir.
And you have to make their GUI, and you have to export those things, and in this Tanner you can import those things. So you have to use 2 tools at a time simultaneously, back-end tool as well as front-end. So
Yes.
back-end tool, you are able to develop a PMOS by import those things in Tanner. Whatever you design in Tanner, those based MOS and
Yeah.
T4.
Sir, it is possible.
In this one is older one. It is freely available, and 250 nanometer no one is working on right now. So if you will go for the licensed one, then you will have in our lab we are having the licensed one, where we are having 45 till 45 nanometer we are having in our lab.
Okay, sir. Okay. Thank you so much.
Any other questions from participants?
Any other
Good
questions
evening,
from
ma'am.
participants?
This is Dr. Ravi. Shall I ask one doubt?
Yeah,
Sir, good
yes,
evening, sir.
yes,
Your hands-on
Yes,
training is
please,
very
yes.
nice, and also you have explained very nicely for the Tanner tool. Sir, I'm having one doubt because I'm working in Synopsys, HSpace tool. So in that, if you want to measure the delay, we can go for a separate tool like Osmoscope. Like that, if the